Hello everyone, in this video I would like to show you how you can solve the inverse dynamics problem for a 3-link RRR articulated robot arm using the Lagrangian approach. So RRR basically means that it has 3 rotational joints, so maybe let's look at what it might look like. So here is our structure. It has 3 links and there are only rotational joints. So the first rotational joint would be along this vertical z-axis. The second joint is between link 1 and link 2, and the third rotational joint is between link 2 and link 3. So that's the general idea. And of course you could modify those angles as you wish, and it would be displayed in a different position here. So this is just here so that you can have an idea of what it looks like or might look like. Okay, so we're treating those links as cylinders. So not as slender rods, but cylinders. That's a bit more complicated, but not too complicated, so don't worry about that. Anyway, let's go back to Python, and here we're gonna use some modules like SymPy, just like before, some classes, some methods from the mechanics module, also NumPy for numerical calculations, and matplotlib and related tools for plotting. And here again I have this helper function to help me display some of the results in a nice way and with LaTeX formatting. So first things first, we're gonna have to, well, maybe let's run those cells for now, and now we have to define the necessary symbols and functions. So each one of those links has some mass. Notice that the radius of each of those links is the same, so the radius is shared among the 3. So we have M1, M2, and 3. Those are masses, which in this case, really apply to the centers of mass. And then we have the lengths of the links. So L1, L2, L3. R stands for the radius of the cylinder or the link. G for gravitational acceleration, and T for time. So those are our symbols. And then we have the joint variables. So theta 1, theta 2, and theta 3. We use the dynamic symbols function to help us define them. And I'm writing them down in full because then it's going to be formatted nicely with LaTeX if you do it this way. Okay, so let's run this cell as well, and then we proceed to define the position of the centers of mass for the second and the third links. Notice that I skipped the first link. That is because essentially the first link has no kinetic energy related to translation. So the only kinetic energy we can notice here is that related to its rotation about its vertical axis. So basically if you look like from above or from below, then you can notice that it's pretty much a disk. So this is the only kinetic energy it will have. So we have to account just for that, but we don't really need to define all the positions, or I mean all the components, the X, Y, and Z components of the position of the first center of mass, because there's no real translation going on here, just rotation about its vertical axis. So that's why we go straight to X2, Y2, and Z2. We divide those by 2. Notice that we do it here because assuming that the link is uniform, that the mass is distributed evenly along its length, then it's located at the center here, halfway its length, and also the center of this circle if you were looking from this angle, right? So that's the idea. Okay, so let's go ahead and run this, and then we go to the position of the third center of mass. We cannot really use this here because this is divided by 2, but in order to get to the third link we have to cover this entire distance from, let's say, point A to point B, and then we go to the third center of mass. So that's why I cannot use this equation here directly, right? So and to that I add L3 times cosine theta 3 times cosine theta 1, because as you can see everything is pretty much dependent on theta 1 as well, because when the first link rotates about its vertical axis, then the whole structure rotates. Yeah, so I kind of treat it like a union here in OpenSCAD, so to reflect that dependency. Okay, so actually instead, yeah, I'm not going to split it up because of the 2 here divided by 2, so I'll just keep it in this form. So let's run this piece here. And now we can differentiate those components of the positions with respect to time. So let's do that, and let's display the results. It looks more or less like this. I'm not really using any simplification here, so I just display those just how they are in its default form, or in their default form. So here I'm run the other part of the script, which basically differentiates the positions, or the position of the third, or the components of the position of the third center of mass with respect to time. So this is what it looks like, more or less. And as you maybe remember from one of the previous tutorials, one of the previous videos, I introduced the concept of inertia matrices. So maybe it's not very readable in this form, so let's run this cell and see what it looks like. So this element here on the main diagonal is basically the same as this one, which kind of makes sense because, you know, you can rotate a cylinder along or about the x-axis, or in this case y-axis, in the same way as you would about the x-axis. But if you rotate it about the vertical axis, then it's like rotating a cylinder. So that's why you have here this element that looks just like the moment of inertia for a cylinder about its center. Sorry, I meant like disk, basically a disk. So this is equivalent to rotating a disk about its center. And here it's just the same, like almost the same, because we just change this index 2 to 3. So wherever you have 2 here, we have 3 in the other matrix. Also, I'll introduce some shorthands for the derivatives, so it's easier to use them in the code. So let's do that. And then we introduce angular velocity column matrices. So actually, instead of this, I could use this part here. And the first derivative of theta 1. And here, theta 3. And again, the first derivative of theta 1. So let's see what it looks like. Okay, I forgot the square brackets. So let's do that. Okay, so this is what it looks like. And then we compute the kinetic energies for the structure. So for the first link, it's just, you know, as if you were calculating it for a disk. So it's m1 times r squared times theta 1 dot squared, and you divide everything by 2, as you remember in the formula. And then you have the second kinetic energy. Here we also perform some simplification, and we have to include the rotational component and also grab the first element, because it doesn't return a scalar but rather like a list or a matrix. So you have to extract the first and only element in this case from this matrix. Same with the third kinetic energy. So let's just run this part and see what we get. Okay, so this is what it looks like, more or less. We're not really gonna analyze those equations. Let's just assume that they are correct, which they should be if we didn't make any silly mistakes. Okay, so now potential energy. We can try to display them as well. So let's try to do that so that we know where we are in the process. So this is what it looks like. Okay, and now we're good to go. We can express the Lagrangian function by subtracting from the total kinetic energy, which is the sum of the those three energies, EP1, EP2, EK1, EK2, EK3, minus those three potential energies, so EP1, EP2, and EP3. So let's run this part as well, and here's our Lagrangian. Doesn't look too pleasant, but the structure is a bit complicated, so that's probably why. And now we can use the Lagrange's method class to derive the equations of motion. So let's do that, and let's display them as well while trying to simplify them. Okay, so this is what it looks like, more or less. So as you can see, we have those torques here. So the first torque, the second one, and the third. And this is the formula that you can use to actually get those torques. And that's what we'll be doing here. Okay, so the next step is to turn those equations of motion into functions that take numerical values. And for that purpose, we use the lambdify function from the SymPy module. So we introduced those parameters that will be used in this lambdify function. So I just named them T1 lambda, T2 lambda, and so on. So each of those equations, because as you can see, it's like a list or like an array. Then I have to grab the first element, so which is the first equation, second equation, and the third equation. And basically now I have functions that I can actually use to perform numerical computations. So since we've already done that, we can safely introduce numerical values here. So the length of the first link is half a meter, and then we have 0.7 meters and 0.6. The radius is basically 5 centimeters. The first mass is 1 kilogram, then you have 1.4, 1.2, and for gravitational acceleration we put in 9.81. Okay, so if you were wondering what this part is doing here, this box, like, you know, this gray box, it's basically it defines a space in which our trajectory lies. So this is just to help us visualize whether this trajectory can be reached by our or each point of this trajectory can be reached by our robotic arm. So this is the purpose of this gray box here. And as you can see, even visually, of course, you can try to calculate it somehow to be sure that, it always falls into that region, into that space. But even visually, you can inspect this and see that it should be able to reach every point within this box. So with that being said, we define a general shape of our trajectory. So we just assume some angle, use the cosine and sine functions to kind of make it look like a real trajectory. So let's run this piece of code and see what we have. So imagine you have one point here, like point A. You pick up some object, and then you go all the way up here and you place the object somewhere here at point B. And this is actually not just like an arc, but it has some deflection also if you look from above. So let's look at it like this. Yeah, so as you can see, it's not like a straight projection, it actually is more like a curve here. Okay, so this is a pretty interesting trajectory for our purposes. And now, as you can see, that is the general shape, so we didn't worry about the limits here so much. We just wanted to have some shape. But now we're going to use this helper function called fit to help us fit the not the directory but the trajectory into a box within our workspace. So that gray box that you saw not so long ago, we're going to run those coordinates, so x, y, z, the coordinates of the end of this third link, the last link. So let's run this and see what it looks like, more or less like this, which corresponds to our box right here. Okay, so once we have this, we can go to the next step, which is converting the trajectory to the joint variables. So we go from the trajectory points to the joint variable values, basically. So here we have just a drawing to help us understand what's going on, even though I'm not going to go into much detail on how it's done. But basically, you can think of the second link and the third link as the radii of two circles that intersect. So they intersect at point B and this point here, which would be like B prime or something like that. But that's the general idea. But of course, if you look at the model here, this other solution doesn't really make sense, because this part of the second link as well, this part of the third link would probably go out of the workspace. So it doesn't really make much sense to do it that way. This is why we're going to exclude or discard that other solution, which is going to use the one that approaches this box from above. So the trajectory will be followed from above by this tip of the last link. Okay, so here basically have some parameters derived based on the assumption that those two circles have to intersect. So we have to write down two equations for circles and form a system of equations, and then we solve the system of equations, and this is more or less what we get. So we calculate the delta and we find one of the roots because the other one is not needed in our case. And also, in order for the third angle to correspond to this drawing, then we kind of have to add a minus here to make it look like it's under this horizontal line rather than above. So it depends on the direction that we have here. So we kind of compute it for this, but then we want this value. That's why we add a minus here. Okay, so let's run this part of the code. And by the way, if you need some further explanation of what I haven't managed to cover in this video, then feel free to ask in the comment section, and I'll be happy to help. Okay, so let's run this cell, and the next step is to introduce like an array that represents our simulation time and also the time step. So the time step would be the difference between, in this case, between the second element and the first element, because they're spaced linearly, so the distance should be the same. Of course, because of floating point rounding errors and arithmetics, stuff like that, we don't necessarily get precise values every single time, so it's best probably to pick those first two elements because they're less error prone. Okay, so let's run this part. So we're going from 0 to 10 seconds, and we are gonna have 1000 points because that's the length of x. So it's good to make it correspond to the number of points of your trajectory, so the same number of time steps. Okay, and now we have this interpolate helper function that you've probably seen before if you've been following my videos. So let's run this part as well. This is going to help us get back that one element that we lose each time we differentiate numerically. So this is what we have to do. So we differentiate theta 1 with respect to time numerically, of course. So we lose one element and then another one. So in order to get it back, we have to interpolate. Yeah, because in the next step, where we have to input those numerical values into the previously generated lambda functions, or those functions generated by the lambdify function. Well, we can have like scalar values, like singular values, like m1, m2, l1, l2, and so forth. But if you have like an array of values, like, or a list of values, then the length of those arrays and those lists have to agree, which is why it's important to make sure that the number of elements is the same in each of those arrays. Okay, so with that being said, let's run this part of the code, and hopefully now we can plot something. So we're going to plot the first torque against the simulation time. So we're going to see how it behaves over time as we go from, let's say, point A, point B, where we want to, move our object. Okay, so this is what it looks like. As we can see, the values are very small, almost to the point of being negligible. This kind of makes sense because we're not really assuming any friction, any sort of thing like that. So basically, the torque that is necessary to turn this whole thing around shouldn't be too high. It doesn't have to support anything, so it kind of makes sense logically. So that's, one thing to check. Like, even if it, if you don't know what to expect, like what shape of to expect on this this plot, then you kind of have a general idea of whether it makes sense, like in terms of magnitude. Okay, so now let's plot the second torque. It looks more or less like this, goes from almost 10 down to almost 3, and then goes back up again. And also let's look at the third torque, and here it's like kind of the inverse. It goes from a lower value to a higher value, and it goes back down to a lower value over time. And as you can see, the maximum value here is almost 10, just like here. Maximum value here is roughly 2.2, which again kind of makes sense, because the second link has to support not only itself but the third link as well. So it's kind of expected that at least at some point it will require significantly more torque to be able to do that. Okay, so I think this is the end. Well, I hope you find this video useful. If you do, please leave a comment, hit that like button, subscribe to my channel, and I hope to see you next time. Bye.